Right. So, we have been seeing quite a few concepts based on third module, right, with respect to space link, and we've seen the factors associated with respect to noise, right? Uh, we have gone through few equations, and we've also solved few problems based on those. Most of the problems here are going to be very simple, as I mentioned, right? It's just going to be substitution of data, and the catch here is, you should know which formula to substitute, because we are learning a lot of formulas here, right? So if you can filter out one particular formula, right, so then that will be fine. So the best way to do it is, you can take the data available in the question, and if in case there are some constant values, then you can assume them. If not, then you can use the standard values. Okay, so we have to start with the noise temperature of absorptive networks. So not only this noise spikes up in the waveforms as we see, but then it can also create temperature. So as I mentioned, this is going to be denoted as Tn. Okay, fine. So the absorptive network is one which contains resistive elements. So when I say resistive elements, it contains resistors, coils. These introduce losses by absorbing energy from the signal and converting into heat. Okay, so this is important, where we try to understand that the conversion, what is the end product. Okay, the end product is going to be nothing but the heat. Okay, so it introduces losses and it converts them to heat. Fine. So resistive attenuators, transmission lines, waveguides are all examples of these types of absorptive networks. And even rainfall, which absorbs energy from radio signals passing through. So usually, you would have seen whenever there's rainfall, okay, your television signals, or it could be your radio signals, okay, wouldn't be that proper. Okay, so that's because of the absorption that happens. So together, we term this as absorptive networks. Okay, because of an absorptive network contains resistance, it generates something called thermal noise. So thermal noise is generated, and because of which this noise is getting associated with our communication signal, and it is hampering the way we process things. Okay, so moving on to the next concept, right, where we are considering a network, okay, and this has a power loss L. Okay, so make note, power loss is going to be capital L. Now, what is a power loss? Power loss is nothing but, is simply the ratio of input power to output power, and will always be greater than unit. Right. So let us now consider a network. Okay, and as I mentioned you many times, whenever there is communication that happens from one end to the other, the inductance should be matched. If suppose there's a mismatch of this inductance, you will hear echo on the other end, right? So you will be able to hear your own voice. So that is because of this mismatch of inductance. So matching networks becomes an important factor. Okay, so I'll be showing you in the next slide the diagram, okay, as to how this is. Yeah, so here you can see the radiated noise, okay, and this is our lossy network. Okay, so power loss L, capital L, is to 1. Okay, and this is the resistance with respect to temperature, and the ambient temperature starting from here to here. Okay, fine. So let the network be matched at both the ends to a terminating resistor. So this is nothing but our terminating resistor. So we are trying to match, the input side and the output sides to make sure that, this is a matched network. Okay. And let the system be at some ambient temperature Tx. So usually we used to take, room temperature, and we used to take about 273 Kelvin, right? But here we are just assuming that it's a normal ambient temperature, right? So the noise energy transferred from RT, okay, into the network is K into Px, okay? So the network noise be represented at the output terminals, and the terminals connected to the antenna by an equivalent noise temperature Tn. Okay, so we connect an equivalent noise temperature, which is denoted as Tn. So Tx is nothing but your ambient temperature, some random temperature we are assuming. Okay, and this is nothing but the radiated noise, and this is the matched resistor. Okay, so what we are trying to do here with the help of this resistor, we are trying to match the input side and the output side. Why is it so important? Because networks need to be matched for proper communication. Okay, so the noise energy radiated by antenna, how do we represent it, right? So you can take down this formula, right, where the radiated noise is K into Tx divided by L. L is nothing but your loss, and then K Tn W naught. So since we have a matched network, okay, we have a matched network. So Tx, which was called your ambient temperature. Remember, we saw ambient temperature is represented with Tx, right? So the available noise energy which is fed into the antenna and radiated is Nrad. Okay, so this is what is the radiated power, Nrad. So this is nothing but K into Tx. Okay, keep in mind that this antenna resistance to which the network is matched is fictitious, which means this may not be the only term. Okay, there can be something else also, right? There can be something else also. So if I say it is only equal to this, that's not the truth, right? As we know that losses can be happening due to various factors, right? So I cannot say it is just K into Tx. Okay, in the sense that it represents radiated power, but it does not generate noise power. Okay, so radiated power. So here we are only concentrating on radiated power. This expression for Nrad, okay, can be substituted in the equation. So we take this Tn, okay. Now again, Tn has a breakup here, right? Tn has a breakup, which is nothing but Tx into 1 minus 1 by L. So this is the most simplest form that we can come across. Okay, Tx into 1 minus 1 by L. So Tx value will be given to us either in the question or it will be told to assume. Okay, and of course if we know the losses, okay, then it's going to be easy for us to do it. Just a moment. Okay, so the next thing that we'll be seeing here is how can we make this formula, right? We have this 1 minus 1 by L. How can I make this formula more simpler? Okay, so I can just take it as L minus 1. So we'll see that. So the equivalent noise temperature of the network, which is referred to the output terminals of network, the equivalent noise at the output can be transferred to the input, dividing the network power gain by 1 divided by L. So that is what we actually saw here, 1 by L. Okay. So thus the equivalent noise temperature of the network is referred to the network input and be slightly modified. Okay, we modify it as L minus 1. So you can take down this formula as well. Okay, so basically here you have to remember the formulas, right? So since the network is bilateral, so whatever equations we saw, which is 1 minus 1 by L, and this equation here apply for signal flow in either direction. So since it's a bidirectional, uh, which means input can act as output and output can act as input. Okay, so whenever we are dealing with antennas with respect to satellite, as I mentioned, they just cannot act as transmitters, they just cannot act as receivers, but then they act as both, right? So yeah, so we need to have it work as uh, the bilateral form. Okay, so this gives us the equivalent noise temperature of a lossy network, so which is referred to input at the antenna when the antenna is used in receiving mode. So the antenna can either be in receiving mode or it can be in transmitting mode. Okay, so moving on, remember I had told you about noise figure and noise factor. I hope you all remember that, right? So for noise figure, okay, we use this kind of nomenclature, and noise figure is going to be 10 log of F. So what is F here? It's a noise factor. Okay. Right. So if the lossy network should happen to be at room temperature, let's assume that it's about like 19 or 20 degrees, okay, then we can term it as T naught, okay, and our noise factor, okay, is going to be F is equal to L. This shows that at room temperature, the noise factor of a lossy network is equal to power loss. So only, you look for, the question, and then if it says it's at room temperature, then your formula becomes as simple as F is equal to L. Okay, so this happens only when we are operating at room temperature. If suppose it's not at room temperature, then what would you do? You have various challenges and you'll have to use different formulas, right? So now, as I told you, right, we have to calculate the overall noise temperature, not only because of the transmitter, but also because of the receiver. So here you can see that, we have amplifier 1, okay, and then here we have another amplifier, okay. So this is nothing but low noise amplifier. The reason why we are using a low noise amplifier is because the noise signals should not be amplified, at a higher level, right? So if noises are amplified, then what about the communication signal, right? So even those signals are lost. So as much as possible, we make sure that we try to maintain a lower amplification, especially for this noises. Okay, and this is going to be your cable. G1 is the gain. Okay, TE is the equivalent temperature that we saw, right? And this is the antenna's temperature. Okay, T and receiving at the receiver side, the noise factor F. Okay, so these are the connections used, okay, for calculation of overall temperature for a system. Now this formula is important, right? Where we have the system noise. Okay, many problems will come up based on this formula. Right? So all of you can make a note of it. Okay, TS is nothing but your system temperature. So the whole thing. So this is comprising of the antennas, the equivalent temperature, considering the losses, the gain, okay, at ideal temperatures T naught, okay, and the noise factor F. So the significance of this individual terms, okay, we will be seeing that in the example. Okay, so we will solve some example, and then you will be able to understand how this is done. Okay. Right. So if you see this example here, okay, we are trying to consider the same figure, okay, which is the previous one. Yeah. So we are referring to the same figure, and based on this figure, we are having this example, okay, where the receiver noise figure. See, I've directly given you the values, right? So the receiver noise figure is going to be about 12 dB, okay, and the cable loss, okay, is going to be about 5 dB, and low noise amplifier is about 50 dB, okay. That's the gain, so you can take it as G, and noise temperature, which is Tn, is 150 Kelvin. The antenna noise temperature is 35 Kelvin. Okay, so this is uh, antenna noise. Okay, so T ant. So for T ant, you can give this value. So here your motive is to calculate the noise temperature, which is Tn. Okay, refer to the input. So we can use the formula for TS, okay, which is nothing but your system temperature, or system, the total overall system noise. Okay, so we have to make slight changes here. Okay, so we have about the noise factor and the noise figure, the 10 log thing that I mentioned. So this is what you're going to do. So F is going to be converted into noise figure, right? So which is about 15.85. Remember, students, this thing is important, right? Because I've seen most of the time, mistakes happening just because you have not done this conversion. Okay, so just make sure that you have 10 raised to 1.2. Since it's 12 dB, here you're dividing it by 10, so it becomes 1.2. So 10 raised to the value which is divided by 10. So you are converting the factor, okay, into figure. So that's 10 raised to 1.2. Similarly, this is again going to be divided by 10, so 5 becomes 0.5. So 10 raised to 0.5 yields you this value. Okay, then again gain 50 divided by 10, so it gives you 5. So try to understand a pattern here, right? We are trying to convert them into the same forms. Okay, so the direct value is given here, which is 35, right? So we just take it down, right? 35 is taken down directly. Then I have 150, right? 150 is also there, and I'm going to make use of these values. Okay, L minus 1, L minus 1. Okay, and remember I had told you we are going to use about 290, right? The standard value 290 temperature, and similarly 3.16, then 15.85 here, the noise. Okay, F minus 1, and then T, which is 290. So the same T here we're going to use. So approximately, we're going to get the value of 185 Kelvin. So how do you solve this problem? First, what you can do is, probably you can take this as an inverse, okay, and then you can multiply it with 290. Okay, you can have this value and multiply that value along with 3.16. Okay, so if not, you can do another step where 3.16 into you minus this one. Okay, so it becomes 14.85, and you can keep the whole numerator as one number divided by the denominator. So that is one way, and here you will have A, and here you will have B. So A plus B plus 35 plus 150. So that should give you the whole value, which is about 185 Kelvin, right? Simple problems, but then I have seen that most of the you know mistakes happen when this conversion uh, doesn't reflect. Okay, so these conversions are important. Fine. Okay, so we're going to use the same, and we're going to calculate when it is rearranged. Okay, so we're going to go back to the same figure is arranged in figure B. So let us now go back to figure A and figure B. Now, if you see here, antenna is there, antenna, and then immediately you have a low noise amplifier. After low noise amplifier, you have a cable and then receiver. So here we have made some rearrangement. So antenna, cable, after cable, low noise amplifier, and then as usual the receiver. So by making these changes, these rearrangements, we will see what is going to happen. So here, for the figure A, we had calculated it was about 185, right? So we had got about 185 Kelvin. So now with respect to figure B, okay, we will calculate. Okay, so similarly I have these values, okay, 35 and then 3.16 minus 1, this value we have taken from the previous one, L. Okay, L is nothing but 10 raised to 0.5, which is 3.16. So that is taken here, and you can see that 1136 Kelvin just because of this rearrangement. Okay, so what do we understand? Even though the components used are same, okay, even though you see that we have T and we have LNA, we have cable, and this loss is L is to 1, and then we have a receiver having noise factor of F. Even though all the components are same, just because of the rearrangement, right, there can be a huge impact. So where is 185 and where is 1136, right? Okay, so this is your takeaway, your final takeaway. Okay, the one that I have mentioned here, okay, in the last is the final takeaway of the comparison that we have done with figure A and B. So it illustrates the important point that LNA must be placed ahead of the cable. Okay, so which means before the cable, we place the LNA, low noise amplifier, and then connect it to a cable. Okay, so that is one of the reasons why we see amplifiers mounted right at the dish in the satellite receive systems. Okay, so the same concept is used with regards to our DTH. Okay, right. So the next thing that we'll be looking into is carrier to noise ratio. Okay, so what is this carrier to noise ratio? As we all know, the short form of this is going to be CNR. Okay, C is referring to carrier, N is referring to noise, and R is referring to ratio. Okay, now we'll be dealing with noise power, okay, receiver power, PR, and yeah, we'll be seeing few more CNR concepts with respect to uplink and downlink. Separately we'll be seeing uplink, and separately we'll be seeing downlink, and then we will have something called combined PNR, combined CNR, okay, which is having the uplink and downlink together. So a measure of performance of satellite link is the ratio of carrier power to noise power. So how much of signal that I am able to transfer and how much of noise is actually getting added. So do you think systems with more noise is good, or do you feel that systems with less noise, or let me put it in a simple way, is noise a good factor? Is noise a good factor?
No, sir.
Yeah, so as much as possible we make sure that we don't want any noise. Okay, and we make sure that these noises are nullified as much as possible, right? Okay, So that's why, we saw that few rearrangements were done previously, right? Rearrangements were done, and we were able to, really crack it out, with the 185 and 1136 with the rearrangements. See, this is why problems are important, where you understand, you get them in the form of numbers, and you calculate, and you try to understand, what exactly is to be done, right? So conventionally, the ratio is denoted by C slash N, okay, or we can put it as C by N, okay, which is equivalent to PR by PN. Okay, so this formula is important. So carrier to noise ratio is equal to PR minus PN. Okay, so whatever you have received minus the noise. Okay, few more equations to concentrate on. Okay, you have EIRP, which is equivalent isotropic radiated power, then gain of your receiver, then losses. As I mentioned previously, losses is a huge term. It has many terms involved. Okay, so let us just recall them. I will just take you a little back where we saw, noises had various components, right? So it has FSL, okay, it has RFL, okay, antenna misalignment, okay, atmospheric absorption due to polarization, okay, free space loss, okay. So it has a lot of things involved, okay, feeder loss, receiver feeder loss. So all these are part of losses, okay. So it's a huge concept. So you can just check what is mentioned in the textbook, in the problems, and try to extract data from those exercise problems, and you can start solving them. Okay, fine. So your carrier to noise ratio is going to be EIRP plus gain minus losses, Boltzmann constant, system, your system temperature, okay, and the bandwidth of noise, the bandwidth how much is allocated for noise. Okay, so you can just write what these terms are referring to. Okay, so we have another term here, which is G by T. Okay, G by T, gain divided by those temperature, and this is going to be your final equation. Okay, C by N is equal to EARP plus G by T minus losses minus K minus BN. Okay, please make a note of this. We'll be using it for our problems. Okay, make a note of this. So carrier to noise ratio, the final equation. Okay, this is what we're going to use. Okay, so it's a combination of EIRP, it's a combination of gain, losses, Boltzmann constant, bandwidth allocated for noise. Okay, so these are the terms involved. Fine. So now, we'll try to have a small breakup of them, and we will try to understand what these terms are referring to. Okay, the ratio of carrier power to noise power, okay, that is C by N, okay, maybe actually required, since Pn is equal to KTN Bn. Okay, so K is your Boltzmann constant, Pn is your noise temperature, Bn is the bandwidth allocated for noise. Okay. So accordingly, we have written this formula, right? So C by N naught, okay, minus Bn. Now remember all these, it's with respect to dB. Okay, C by N is a true power ratio in units of decibels, and Bn is the decibel relative to 1 hertz. Okay, 1 hertz relative to 1 hertz is kept into consideration. Okay, so now you might even see, N naught. Okay, N naught. So these are also in terms of dB hertz. Suppose, we try to substitute whatever value, okay, whatever terms that we have got here with this 12.37. Okay, so we should be arriving at a final formula, which is C by N naught is equal to EIRP plus G by T minus loss minus K. So in the problem, they would have mentioned antenna misalignment loss, feeder loss, receiver feeder loss, free space loss. So just check what is mentioned, and accordingly you can substitute for all those losses. You can add them up and together, put one term here. And of course we know Boltzmann constant, right, which is about 226 to 28 minus, right? So minus minus becomes plus. Okay, so this is one of the best example, where we can understand the application of the formula that we have seen so far. Okay, so we have a link budget calculation. Okay, and we are using a 12 gigahertz. So 12 gigahertz, which is the C band. Okay, and the free space loss. Okay, FSL is going to be about 206 dB. Okay, the antenna pointing loss. Okay, so you have to keep making note of this. FSL is 206, and the antenna pointing loss is going to be 1 dB. Then atmospheric absorption AA, I just showed you, right? So it's going to be 2 dB. Then the receiver is 19.5 dB per Kelvin. Then RFL, receiver feeder loss, is also given here, which is 1 dB. Then EIRP is also given directly, which is 48. Calculate, CNR. Okay, so what we do is we take Boltzmann constant. Okay, so as I mentioned, it's about 228 decilogs. Okay, and the best way to solve these kind of problems is we will tabulate them, right? We will put them in the form of tabulation, and we will try to calculate them. So free space loss, the given value was 206, right? So we take it as 206. Atmospheric loss, pointing loss, all these are losses, right? So minus, and polarization, nothing is mentioned, so I will just take it as 0. Okay, then your receiver G by T ratio is going to be 19.5. Okay, EIRP is 48, and minus K, which is your Boltzmann. So since I've taken minus here, I'm not mentioning that minus here with this number. Okay, if not, then this minus will come here. So I'll be just mentioning K with the square bracket, and this becomes minus 228.6. Okay, then C by N naught is about 86. Okay, we have not mentioned it here. 86 is not mentioned. It's taken as a value based on the previous equation. Okay, so if you find if you try to calculate all of this, okay, so that's how you will get 86.1. Okay, so you can put them in the formula, right, which is 12.38. This is the final formula, right? So EIRP value we have, G by T we have, losses we have, and minus K. So try to put in those values and you'll be getting about 86.1. That's it. So next we'll be looking into uplink, and we will see exclusively with uplink how these changes are happening. So we have seen this problem, right? So next we will continue with the uplink. Okay, so as I mentioned, CNR, okay, it's not only with respect to only pertain to uplink or only to downlink, okay, but then it's a combination. So first we will look at uplink, and then we'll go into downlink, and then we'll combine them both, and we call it combined CNR. Okay, so you can see these subscripts here. So this is referring to, so we are using the same standard formula that we used previously, right? And this U is referring to the values, okay, which is with respect to uplink. Okay, fine. So the uplink of a satellite circuit is the one in which the Earth station is transmitting the signal and satellite is receiving. So we are sending signals from the Earth to the satellite, which means from the base station to the satellite. Okay, so U, the subscript U is used, as I mentioned, right? So in this equation, the values are to be used as the Earth station EIRP and satellite receiver feeder loss and satellite receiver GT, okay, that value, then free space loss and other losses. So all this will be with respect to the Earth station, okay, with respect to the uplink frequency. The resulting carrier to noise ratio density, okay, will be, so this is going to be the formula that you are going to use. Okay, so you can just note it. This is the formula. Fine. So in some situations, the flux density appearing at the satellite receive antenna is specified rather than the Earth station. So sometimes, what is given here is, sometimes specifically the flux density values, okay, which is 5. Okay, so that will be mentioned. Okay, if it's not mentioned, then fine, no problem. You can use the values which are given. Okay. Right. So saturation flux density. Okay, so we'll be learning about this. We saw this traveling wave tube amplifier. Remember, the electrons were bombarded, okay, and they were passed into coils, and then they were tried to make, a laser type of electron gun. Okay, so this is what is referring to DWTA. So in a satellite transponder exhibits power output saturation. So we will see that figure. Okay, I'll be showing that at a later point. The flux density required at the receiving antenna to produce saturation of DWTA is termed as saturation flux density. Okay, so the flux density required for the antenna which is at the receiving side to produce saturation. Okay, to produce saturation, so which means it should get into saturation. So you have seen this diagram previously, right, where we have seen this traveling wave tube amplifier. Okay, let me just bring it across. Right, traveling wave tube. Okay, so here we have heater, cathode. Okay, so these are all the helix cables. Okay, we are here, we're trying to get these electrons as, as a small beam, just like an electron gun. Okay. So done with this. Okay. So the saturation flux density is specified quantity in linked budget calculations, and one can calculate the required EIRP at the Earth station. So this value also will be given. Okay, and you can calculate the required EIRP. Okay, fine. Now, how are these terms? How is this flux density, relating with respect to EIRP? Okay, so this is the formula. Okay. Your maximum flux density, okay, M is your maximum flux density, okay, EIRP divided by 4 pi r square. Okay, if I take it with respect to dB, okay, then EIRP plus 10 log 1 by 4 pi r square. Free space loss is equal to 10 log lambda square divided by 4 pi. Okay, so take down this formula, right? So this becomes an important one, where it represents EIRP and free space loss. Okay, and Just a moment. Okay, so this is going to be your final form, okay, of flux density. So we have this term lambda squared divided by 4 pi. So this is nothing but relating to how your antenna is, what are the dimensions of your antenna, okay, and A is nothing but the effective area, okay, and 4 pi, the dimensions of your antenna. So now A is equal to 10 log lambda squared divided by 4 pi. So I can put this as A naught. So this lambda squared divided by 4 pi, I can put it as A naught. So if I want to bring it in terms of numbers, right, 21.45, you can just make note of this, right, and the frequency is going to be in gigahertz, of course. If not, then our transmission wouldn't happen. Okay, now EIRP is a combination of all of this, your flux density, okay, then effective area, which is A naught, and free space loss, okay, free space loss. So my final EIRP, is going to be a combination of all of this, right? Flux density, A naught. A naught is nothing but, this term lambda squared divided by 4 pi. Okay, so this is nothing but the effective area. And then FSL, EAPL, and misalignment loss. So if the antennas are not aligned properly, that's what we get. So with respect to losses, okay, we can just term all of this with losses, okay, and we can generally put it as loss and just keep receiver feeder loss A naught and the flux density separate. Okay. So our final uplink EIRP, okay, if a question is asking to find out EIRP for the uplink, you'll be using this formula. Okay. Fine. So take down this example where it's operating at, see, the uplink operates at 14 gigahertz. So 12, 14. So 12 is the downlink and 14 is the uplink, right? So here directly in the question we are seeing 14 gigahertz. So which means this is referring to the uplink, and the flux density required to operate, required to saturate the transponder is about 120 dB. Okay, so that is your phi m. Okay, your psi m. The free space loss is going to be about 207. Okay, FSL you can take it as 207, and the other propagation losses. Okay, so on the whole you can take it as loss is 2 dB. So you need to consider this as well. Okay, so calculate the EIRP. So we're going to use this formula here, EIRP, right? EIRP required for saturation, assuming clear sky conditions. So which means there is no atmospheric loss. Okay, and we are also nullifying RFL, which is receiver feeder loss. So we are taking out atmospheric loss, we are taking out receiver feeder loss. So how do we go about? So at 14 gigahertz, first we take the value of A. Okay, A is given here, which is F is already known to us. So 21.45 plus 20 log 14, right? So that will give me my A naught. So I will take that A naught and substitute in EIRP because I need this term. Psi S is also given, right? Okay, and then you have 120, right? You have the same value, you bring it down here, which is 44.37 and 209. How is this 209? You have 207 and you have other losses which is about 2. So you're adding them both. Okay, so it's 207. So finally we get about 44.63 dB watt. So this is how you try to take values and try and understand what is given, what is not given, which formula to use, and how do I substitute values. So once you know this, the rest of the things shouldn't be that complex. Okay. Now we had seen back off. Okay, let me show you that graph. Now where we try to make it into saturation, right? We don't allow it to get into saturation. Let me show you somewhere here around. Yeah. So this power, while we were studying about power amplifier, right, we learned about the output back off and input back off. So we do not want these kind of huge deviations, right? So as much as possible, we try to just have it in this point, okay, so that here we're very close to 0 dB, close to 0 dB, right? So that's the whole idea, right? Okay. So now about input back off. Okay, so the same concept actually, but then we'll be putting it in the form of equations now. So where a number of carriers are present. Okay, so usually you have seen these days MIMO, you've seen OFDM, right? Where we are using multiple subcarriers. Okay, the job is not just done with a single carrier, but then we use multiple carriers. So whenever we have multiple carriers, okay, and the operating point must be backed off to a linear portion of the transfer characteristic to reduce the effects of intermodulation distortion. So as I told you, right, so we had this graph, okay, to show you. So as much as possible, I want to bring it in this level. Okay, so there is no much of deviation. So this is my 0 dB and 0 dB. Okay, so I try to bring it in that level. Okay, so in order to do that, I have the control in the form of input. So either I increase the input. When I increase the input, it probably might come here at this point, and then when I decrease it, it might come here. So I try to fine tune it and bring it somewhere in between. Okay, so that is what it is. So the operating point must be backed off to linear portion of the transfer characteristic to reduce the effects of intermodulation distortion. Okay, so making it a constant one is important for us, right? Why is it so important? Because we do not want so much of deviations, right? We want it to be as stable as possible. Okay, so such multiple carrier operations occur with frequency division FDMA, right? With frequency division multiple axis. So with this kind of technique, we see these concepts creeping in. Okay, which is back off. So back off we denote it with BO. Okay, and this can be either input back off or output back off. So if it's input, then I put it as IBO, I suffix I. Then if it's output, then I put it as BO suffix O. Okay, fine. So your EIRP uplink is equal to uplink minus whatever is the back off value. Okay. So now you can see we are trying to make changes to to the formula, right? We are trying to slowly update the formula, right? Although some control of input to the transponder power amplifier is possible through ground TTNC, okay, input back off is normally achieved through reduction of EIRP of earth stations accessing the transponder. So I'm going to reduce the input levels, and the input back off is going to come into consideration. Okay, so this is going to be your final formula, right? C by N naught for your uplink, okay, then your flux and area back off with respect to input gain, okay, and T temperature, Boltzmann constant, RFL, which is feeder loss. Okay, so let's see this example. Okay, so the uplink is about 14 gigahertz and it requires a saturation flux density of 91. Okay, and an input back off of about 11 dB. So directly you can just substitute this 11, you know, where it says the back off here, right? 11 you can directly substitute. The satellite GYT is about 6.7, so that number comes in here, 6.7. Okay, receiver feeder loss is 0.6. Calculate the CNR. Okay, so AO, we're taking AO minus 44.37. We're just continuing from the previous example. And K is equal to minus 228. Okay, and we'll just substitute them in the form of tabulation as we have done previously, right? So flux density, we have an A naught at 14 gigahertz, right, which was calculated about 44.4. Remember the previous problem, right? We had got about yeah, here we had got about 44.37. So even this was operating at 14 gigahertz, so we don't have a problem. The same band, okay, and you know, this is of course a standard formula, 21.45 plus 20 log f. So f is 14. So we already have this value, so we're just making use of it. If not, then you can recalculate it. Okay. Yeah. So that's how I arrive with this number, which is 44.4, and back off, as I told you, it's 11, 6.7. Just add them up, and that comes to about 74.5. Okay, and this is with respect to hertz. Okay, dB hertz. So the unit, the overall unit becomes 74.5 dB hertz. Remember, in your examinations, make sure to mention these units. Okay, this also will be carrying separate marks. Since fade margins have not been included at this stage, it appears for clear sky conditions. So what do we understand by this clear sky? You know, it just means that we're not considering the losses with respect to atmosphere, right? AA, the atmospheric losses, absorption, AA, we're not taking that into consideration, right? So we are nullifying that. And in one of the problems, right, I think in a previous problem, we had seen that you know, RFL is also neglected, right? RFL is also neglected. So, you know, we'll be giving such kind of inputs in the question. So make sure you take those values and accordingly you try to incorporate it and use this kind of tabulation, right? So that it makes easy for you to calculate. Okay, and just be aware with the minus and the plus, right? So that gives you a proper idea. Okay, fine. So Earth Station HPA. Okay, so the Earth Station HPA has to supply the radiated power plus transmit feeder losses, and here we denote it by TFL. Okay, so this is your transmitter feeder loss. Okay, so when it's in a square bracket, we call it as in dB. Okay, TFL in dB. So these include waveguide, filter, coupler. You know, all these losses can be part of the TFL. Okay. Now, you know, we had used an equation and I have put it as 12.3. Okay, so anyway, so this is going to be your final power, okay, P, which is EIRP minus GT plus TFL, okay, which is transmitter feeder loss. Okay, then at saturation, okay, at saturation, then we will be considering PHPA and BO. Now, what are all of these? Okay, now these are the earth station itself may have to transmit multiple carriers, and its output also will require backoff, and this is denoted by BO. Okay, so the earth station HPA must be rated for saturation power output, and that is given by PHPA SAT. Okay, so the HPA will be operated at the back of power level so that it provides the required power. So, just take down these two formulas, and whichever values are mentioned, either, in the question, if it's mentioned about the saturation, then, you can directly use this. If in case there's no saturation, right, then you can actually use the previous one, okay, which is without SAT, right? So the next is going to be with respect to downlink, okay, and after downlink we will be using the combined CNR, right? Combined CNR concepts. So most of the things here remains the same, right? The formulas, just that the subscript changes, okay? From U it becomes D, and this is CN, which is carrier to noise, EIRP, G by T, and losses and Boltzmann. Everything remains the same, okay? But here the downlink, the frequency would change. Instead of 14, we might use 12. So the downlink of satellite circuit is one in which the satellite is transmitting the signal and the receiver is going to be earth station. But then in uplink, it was the reverse, isn't it? Where earth station has been designated as transmitter and the satellite becomes the receiver. But with downlink, it's the reverse. Okay. So the free space and other losses are calculated for downlink frequency, and the resulting carrier to noise density, which appears at the detector of the earth station receiver. So whatever CNR values that we are going to apply, it's going to be with respect to earth station. Okay. So this is nothing but your noise bandwidth. Okay, BN, sometimes referred to as B. So all this is referring to how much of bandwidth allocated for each noise signal, or the combined noise signal actually. Okay. So a simple example giving us the values with respect to carrier to noise ratio, losses, Boltzmann constant, and the value of B. Okay. A satellite TV signal occupies full transponder bandwidth of 36. We know that, it's 36 plus 4. 4 is, like a guard band. It must operate or it must provide a C by N ratio, okay, at the destination station of about 22 dB. Given that the total transmission losses are 200, so here it's very simple. It just says total transmission loss, so you don't have to worry what is this antenna misalignment loss, what is receiver feeder loss, what is atmospheric absorption loss, right? So on the whole, a figure is given, and you can just use that figure, which is about 200 dB. And G by T is also given directly, which is 31. So you need to calculate the satellite EIRP. Okay, so EIRP formula we all know, which is carrier to noise ratio, right? Then minus GT and losses, okay, plus K, which is Boltzmann, and B. Now remember, we are using plus K, but still the value is going to be minus. Plus into minus is minus. Okay. So the best mode that we do it is in the form of tabulation, isn't it? We put Cn values, we put Gt values, losses together is given. K is your Boltzmann constant. How do we get that? You have your normal Boltzmann constant 10 log and the value of normal Boltzmann. So then B is 75.6. Okay, P is 75.6, and your EARP is going to be about 38. Okay. So if we have to do a conversion, okay, so it's going to be about 6.3 kilowatts, but I suggest, okay, you do not do any conversion. You can just leave it at EARP is equal to 38 dB watts. So that should be fine. Okay, right. So another simple example where we are referring to QPSK signal, okay, and this is transmitted by the satellite, and we are using a cosine wave for that. Roll-off factor RF is about 0.2, and BER, okay, bit error rate. You would have seen this exclusively in your wireless communication subject in your wireless labs, right? So bit error rate, BER, is 10 raised to minus 5. Okay, and yeah, 10 raised to minus 5. For the satellite downlink, the losses amount to 200 dB, and the receiving Earth station is about 32. Okay, and bandwidth, of course, is going to be 36. Calculate the bit rate and what is the ARP. Okay, so I think now, previously I had mentioned that, these values, the value of this bandwidth, okay, the noise is going to be in the range. Okay, there was a range, specific range that the noise bandwidth can occur. So here, in that range, we are assuming it to be 75.6. Okay, so even in your problems, okay, you can take it as 75. Or 75 point. There's a range in which this noise bandwidth is given, okay, from the lower frequency to the higher frequency. So here we are just taking the midpoint, okay, which is about 75.6. So I hope that doubt is clear. Right, so moving on to our next problem, okay, where we are using the same transponder bandwidth, and it's about 36 megahertz, right? Okay, um, just the formulas, right? We sometimes what happens, that portion wouldn't be in your syllabus, but then we'll have to use the formula, right? So you can just make note of this formula. Your the roll-off factor, okay, roll-off factor, and 2 into B is nothing but your number of channels, right? And those are all in megahertz. Okay, 1 plus the roll-off factor. Roll-off factor was about 0.2, right? 1 plus 0.2, so it gives me 1.2. Okay, so this gives me 60. Okay, now if I have to do a conversion, 10 log, okay, Mbps, so 10 raised to 6 per second, so I bring that second down. Okay, so when I convert it, okay, it becomes about 77 dB, okay, bits per seconds. Now for BER was given as 10 raised to minus 5, right? You can see here bit error rate is about 10 raised to minus 5. So EB by N naught. Okay, so again here, we are referring to a diagram, okay, which is a standard value. Okay, so just make note of this constant. EB by N naught is about 9.6. So use that value. So C by N naught, EB by N naught plus RB. RB value we have 60, right? Then EB by N naught value is about 9.6. Okay, so you can just 60 is converted, so I'll be using the 77.78. So EB by N naught is here, and RB value the constant which I was mentioning is about 9.6. So totally it comes to about 87 dB hertz. So this is dB with respect to hertz. Okay. Now, if I have to calculate the EIRP with respect to downlink, so as we know that it's a combination with carrier to noise and G by T, okay, and losses and K. Now, losses he has given directly. G by T is also there, which is direct. Now, C by N. Now, in order to get this C by N is what all this, okay. So, which means you can make sure that this C by N is a combination with EB divided by N naught plus RB. So EB by N naught, okay, how do we get it? 9.6 from the table. You can actually refer the figure 10.17. We are using our prescribed textbook Dennis Roddy for this. So I have mentioned the figure number as well for your further reading. Okay, so from that we'll be extracting the value of 9.6. Okay, so then for RB we have 60. Do a conversion 10 log and 77. So totally, we get about 26.8 dB watts. Okay, so that was our EIRP. So I think we will stop here, and with respect to output back off, okay, we will see in our upcoming classes. Okay.